Imagine a future, right, where our energy grid runs entirely on sunshine and wind. Clean, limitless power.
Sounds ideal.
It does. But here's the catch. The sun sets, the wind, well, it doesn't always blow.
The classic intermittency problem.
Exactly. And this creates a massive energy puzzle, especially, for heavy industries that need constant, really high temperature heat.
Yeah, that's a tough nut to crack with just renewables.
But what if the solution wasn't just, say, more batteries, but something much older, actually, but now ingeniously reinvented?
Okay, I'm intrigued.
Today, we're taking a deep dive into thermal energy storage, TES. It sounds a bit complex, maybe,
A little, perhaps.
but as we'll uncover, it holds immense potential. So our mission for this deep dive, let's unpack what thermal energy storage actually is, why it's becoming so critical right now, and what breakthroughs are really on the horizon.
Good plan.
We've been digging into sources from a recent seminar at Sandia National Laboratories. Big names there, experts gathered to discuss this field.
Ah, Sandia, they do cutting-edge work.
Right, including folks like Scott Hume from the Electric Power Research Institute, EPRI, and Luke McLaughlin from Sandia itself. Okay, let's unpack this.
What's fascinating here is that, yeah, thermal energy storage has historical roots. I mean, humans have stored heat since, well, fire.
Right, basic stuff.
But it's truly an emerging technology now, especially in the context of our modern energy grid, the one we want powered by renewables.
So why now? What's the big driver?
Well, the core promise highlighted in the sources, it isn't just general energy saving. It's a massive unlock for industrial decarbonization.
Decarbonization, okay.
Yeah, it can significantly lower costs and boost the reliability of industrial process heat.
And process heat is?
That's the intense, constant heat needed for heavy industries. Think cement, steel manufacturing, chemical plants, even large-scale food processing.
Huge energy users, often fossil fuels, right?
Exactly. Massive energy consumers, heavily reliant on burning fossil fuels.
Yeah.
And crucially, TES is about its pairing with those variable energy sources, the solar, the wind.
Ah, the connection.
This combination isn't just relevant. It's, potentially a game changer for making these traditionally dirty industries cleaner and cost-effective at the same time.
Which is something other storage, like batteries, struggles with at that scale and temperature.
Precisely. It's a very different challenge than just storing electricity.
That idea of historic yet emerging is really compelling, isn't it?
It is.
It suggests we're not just inventing something totally new, but rediscovering and, vastly improving a fundamental principle.
Right. Refining it for modern needs.
So at its heart, when we talk thermal energy storage, we're basically talking about capturing heat. Could be from solar power, excess grid electricity, maybe even industrial waste heat.
Good point. Waste heat, too.
And then just holding on to it until it's needed. This isn't just, the hot water heater in your basement.
No, definitely bigger scale.
We're talking industrial scale, designed to manage massive amounts of energy. The seminar at Sandia's National Solar Thermal Test Facility, for instance, really underlines that this isn't just theory, it's active research.
Hands-on work.
Yeah. These facilities are literally built to capture and concentrate the sun's power, and then the challenge becomes, how do you use that power efficiently, even when the sun isn't shining, or when an industrial process needs heat during, say, off-peak hours?
Exactly. And the sources emphasize that TES technologies come in a variety of configurations. It's definitely not a one-size-fits-all solution.
Okay, different types then.
Yeah, which is crucial. Depending on the application, you might store heat in different materials, different mediums, and importantly, through different physical mechanisms. We can sort of broadly categorize them into three main types.
All right, lay them out for us.
Okay, first, there's sensible heat storage. This is the simplest one. You're just raising the temperature of a material. Think molten salts, maybe concrete, rocks, even just water.
Like a big hot rock.
Kind of, yeah. They absorb and release heat just by changing temperature, like a giant super hot thermal battery. It's great for high temperature applications, pretty robust.
Okay, sensible heat. Got it. What's next?
Second, we have latent heat storage. This uses something called phase change materials, or PCMs.
Ah, PCMs. Heard of those.
Right. These materials absorb a huge amount of heat when they melt, and then release that same amount when they solidify or freeze, all while staying at a nearly constant temperature.
Like an ice pack, but for heat.
Exactly like that. It offers really high energy density, so you store a lot of energy in a smaller volume, and you get precise temperature control.
Interesting. High density, stable temp. Okay, number 3.
And then there's thermochemical storage. This is maybe the most advanced. It uses reversible chemical reactions to store and release heat.
Chemical reactions, wow.
Yeah, it offers potentially the highest energy densities and can store heat for very long durations, maybe even seasonally, without significant losses over time.
Seasonally. That's huge.
It could be, yeah. Still a lot of R&D there, but the potential is enormous.
That's a fantastic breakdown. Sensible, latent, thermochemical. So it's not just if you store heat, but how you store it. That flexibility sounds like a major advantage.
It really is.
But let me play devil's advocate for a second. Isn't developing so many different storage solutions? Isn't that a bit fragmented? Wouldn't a one-size-fits-all battery solution just be simpler? Why is this breadth, this complexity almost, so crucial for the grid, especially with those variable sources?
That's a great question. And it really gets to the heart of why TES is so powerful in specific contexts. Look, batteries are excellent, truly excellent for electrical energy storage. Grid balancing, short duration is fantastic.
Right?
But they struggle with two key things for many industrial applications: scale and temperature.
Temperature being the big one.
A huge one. Many industrial processes need heat at hundreds, sometimes even over 1,000 degrees Celsius.
Wow.
Temperatures far beyond what batteries can efficiently or even safely provide directly as heat. And these processes need massive amounts of energy, often for extended periods.
Right, not just a quick burst.
Exactly. Thermal energy storage, using its diverse mediums, salts, PCMs, chemical reactions, can meet these extreme temperature demands. It can store that energy for hours, days, potentially longer, far more cost effectively than trying to achieve the same thing with just electricity and batteries.
So it's about choosing the right tool for the right job.
Absolutely. The ability to store heat in these diverse ways is critical because industrial processes themselves are incredibly varied. Making steel needs different heat than pasteurizing milk.
Makes sense.
This flexibility means TES can be tailored, and that's a big part of why it can significantly boost economic efficiency and grid resilience, specifically for these industrial sectors.
That makes perfect sense. It's optimizing the whole energy ecosystem, not just one part. And when we look at the experts driving this, like Scott Hume from EPRO.
Right, from the seminar sources.
Yeah. His background, it says here, is in the design aspects of advanced technology in the power industry. And he focuses on evaluating bulk energy storage technologies with particular focus on thermal energy storage technologies that offer integration opportunities with advanced thermal plant. That really connects, doesn't it?
It absolutely does.
Yeah.
He's thinking about how TA fits into the bigger picture, the grid scale challenges.
The integration piece.
Indeed. Scott's expertise, it mentions over 20 years, highlights just how complex integrating these advanced technologies really is. His work on modeling things like supercritical carbon dioxide power cycles.
Okay, that sounds advanced.
It is. It basically uses CO2 in this superheated kind of liquid gas hybrid state to generate electricity very, very efficiently. It shows his cutting-edge approach. So when he focuses on TES, it's not in isolation. It's about how it can enhance these advanced power plants and the broader grid. He's looking at the whole system, optimizing for efficiency, for sustainability.
And he's a chartered chemical engineer.
Yeah, which speaks to the deep technical rigor needed here. It's not just theory. It's practical engineering for real-world deployment.
Yeah.
He's figuring out the strategic playbook for actually bringing these things to market.
Gotcha. The big picture strategist. And then we have Luke McLaughlin from Sandia National Laboratories.
Right, the R&D side.
Described as a senior member of the R&D staff. His focus is specifically on the development of thermal energy storage technologies and concentrated solar technologies. His work at Sandia's National Solar Thermal Test Facility that really brings the practical, hands-on research into view.
Absolutely crucial work.
It's one thing to design it, right?
Yeah.
But another to prove it works under real conditions. What kinds of breakthroughs is his team exploring there?
Well, Luke's role is all about pushing the boundaries of what's possible. And this is where we see some really exciting stuff emerging.
Yeah.
Sandia's facility is, world-renowned for this kind of testing. And his PhD is recent, 2022. So he's bringing very fresh, cutting-edge academic insights straight into the R&D process. For example, his team is working on next-generation phase change materials, the PCMs we talked about.
Making them better.
Yeah, making them operate at even higher temperatures with greater stability. That unlocks new applications for latent heat storage. They're also developing advanced thermochemical storage systems, using novel chemical reactions to store energy more densely and for longer durations.
The seasonal storage potential again?
Exactly. That could potentially enable seasonal storage for whole communities or industrial parks down the line.
So if I'm getting this right, we're talking about not just improving existing methods, but actively inventing new materials, new approaches to make TES even more efficient, more versatile.
Precisely. It's about creating materials that are effective, sure, but also durable, affordable, and safe for large-scale industrial use. That's key.
So what are some of the biggest challenges they're facing in, getting these breakthroughs out of the lab and into the market?
Well, several big ones. One significant challenge is material longevity and corrosion, especially at those really high temperatures. Molten salts, for instance, can be quite corrosive over time.
Right, things break down.
So researchers like Luke's team are developing new alloys, new coatings to make the components last longer. Another huge one is cost effectiveness.
Always comes down to cost, doesn't it?
Often does. While TES promises lower operational costs, that upfront capital investment can still be a barrier.
Hmm.
So they're focused hard on discovering and validating lower cost, abundant materials that can still perform well.
Cheaper stuff that works.
Essentially, yeah.
Hmm.
Plus, optimizing system designs to cut down construction and maintenance costs. They're also looking at things like modular design, so you can scale them more easily for different industrial needs.
That's fascinating. So you've got Scott Hume thinking about the large-scale integration, the economics, the policy side within the power industry,
The systems view.
figuring out how to make TES a viable part of our national energy infrastructure. And then Lick McLaughlin is actually developing and testing the foundational tech, inventing the materials and systems at a national lab.
Yeah, it's a powerful combination.
It really shows the momentum behind thermal energy storage, doesn't it? This isn't just some academic exercise. It feels like a concerted, two-pronged effort to solve real energy challenges.
Absolutely. And the seminar itself, bringing these different perspectives together, it highlights that energy challenges are complex. They need that breadth of expertise.
And it was open for registration via Teams, the source mentioned.
Right, which suggests an effort to get this knowledge out there widely, underscoring the importance and the accelerating pace of development in this field. It's about moving from potential to actual practical application.
Overcoming those real-world engineering and economic hurdles.
Exactly.
It seems really clear that TES isn't just some niche area anymore. It's rapidly becoming a potential bedrock for our future energy grid.
I think that's fair to say.
From what we've gleaned from the seminar details, these experts are tackling the multifaceted nature of energy demand. They recognize that a truly resilient, sustainable grid needs more than just new ways to generate power,
It needs intelligent ways to manage and store it.
especially for those really hard to decarbonize industrial sectors.
And that focus on industrial process heat is key. They are tackling a segment where massive energy waste and emissions often happen.
Right, the big polluters often.
By providing a reliable, cost-effective, and potentially much cleaner source of heat, TES can have a profound impact way beyond just electricity generation. It directly influences the decarbonization of heavy industry.
It bridges that gap, then, between the variable supply of renewables and the constant high-temperature demands of manufacturing.
That's the goal. It helps smooth things out.
It's genuinely mind-blowing when you think about it, how a concept that's essentially just holding on to heat
Simple idea, complex execution.
can have such far-reaching implications. Stabilizing grids, decarbonizing entire industries. It makes you totally reconsider what energy storage even means beyond just electrical batteries.
It definitely expands the definition, expands our toolkit for energy management. It's about intelligently moving energy through time. Yeah, but in its most useful form for whatever the end application actually needs.
So what does this all mean? We've explored how thermal energy storage, despite its old roots, is really becoming a cornerstone for modern, reliable, and cost-effective energy systems, especially when you pair it with variable sources like solar and wind.
That pairing is critical.
We've unpacked its diverse forms, sensible, latent thermochemical storage, and seen the sheer breadth of its application, enhancing industrial heat, offering grid stability.
Covering a lot of bases.
And we've touched on those exciting breakthroughs coming down the pike, next-gen PCMs, advanced thermochemical systems, all driving down costs, improving performance.
The R&D is moving fast.
And it's all being shaped by the combined expertise of people like Scott Hume, with his deep background in power industry tech and systems integration.
The big picture guy.
And Luke McLaughlin focusing on that cutting-edge R&D material development at a place like Sandia's National Solar Thermal Test Facility. Their work is really driving this innovation forward.
If we connect this to the bigger picture, the work in thermal energy storage, it really encourages us to think creatively, more holistically, about how we manage and store energy. Not just electricity, but energy in all its forms.
Hmm.
And it raises an important question for all of us, I think, as we move towards this more sustainable, more resilient energy future. How many other historic yet emerging technologies, perhaps right under our noses, are just waiting for their moment, waiting to profoundly impact our world, just like thermal energy storage seems poised to do right now?